Last session of the morning, so Professor Xavier CABRÉ is going to continue talking about non-local and mean curvature.
Thank you. Okay, so let's continue. Yesterday, right, we saw a proof of the isoperimetric inequality in Rn with less constant. Then we saw the Michael and Simon and Allard Sobolev inequality, and we proved it in a Rn also. All that was local. Well, in a hypersurface, sorry, of Euclidean space. That was local, everything. And then finally, I told you about the Brendel. That was it, right? Yes. And then the Brendel recent work, where he extends my proof of the isoperimetric inequality now on surfaces, adding some normal variables, and he gets that the Euclidean isoperimetric constant is also good in the isoperimetric inequality on any minimal surface, for instance, okay? And the same for the Michael-Simon Sobolev inequality, at least with p, exponent p equals 1, which is equivalent to the isoperimetric. And when I proved the Michael-Simon, I said either you know Riemannian geometry or you study a little more, and the divergent theorem and tangential derivatives and things like this, or you just use what the Italians, Bombieri, De Giorgiusti used. That is like tangential derivatives. You take advantage to have the normal to be in ambient space in Euclidean space. If you want, you can read Giusti, but there is no need. So I want to say that if you want to fill in details and understand everything in the proof of the Michael-Simon, you can just simply look at the paper I told you of myself with Pietro Viraglio that I gave the reference yesterday. Or I forgot, that's why I'm saying this, or also some lecture notes that I wrote with another Italian, Giorgio Poghesi. And this was in some lecture for a CIME summer school. So these are Springer lecture notes, 2017. And these are lecture notes on, well, also I start with minimal surfaces, the Simon's cone, foliations of minimal surfaces, when foliations by minimal surfaces, the Simon's cone is stable and minimized in high dimensions. So in those notes there are also some geometric stuff. Okay, so that's all what I wanted to say. You can learn these tangential derivatives and stuff here, okay? So now we go to the next section. That will be, next section 3 is the fractional. Now we go really to fractional Sobolev, the fractional Sobolev inequality. It's fractional Sobolev inequality. And geometric, in one shot, we will make it in Euclidean space, and a geometric version of the type Michael-Simon. Not the full Michael-Simon, but well, let's go slowly. In fact, I want to have this here to keep this proposition in the blackboard. I want to keep this proposition, so maybe I can do like this and keep it here. And keep it here. And this will be proposition 4. Okay. Fractional Sobolev inequality in Rn and in hypersurfaces with density. You will see now what I mean with density. To be short, in fact, it's with a lower bound on their density. So what we have is the dimension and a parameter now between 0 and 1, right? that will be the fractional parameter, an exponent greater or equal than 1. And for the Sobolev inequality, we will need S times P less or equal than N. Think that S equals 1 is the local case, okay? And what I have is, like yesterday, a hypersurface in Rn plus 1, so same numerology here, n plus 1, hypersurface. I put it in parentheses because, in fact, it could be a very general set. You will see that the proof applies to very general sets, but let's think that it's a hypersurface. Such that, so this is an assumption, such that there exists a constant, let's call it C star, positive, a constant. I'm going to keep this a constant. And for this constant, what we have is, I look at the measure of my hypersurface intersected with an ambient ball, like yesterday, Bn plus 1, in Rn plus 1, of radius rho, centered at any point of the surface. And I will ask that this is like what it should be for a very smooth, very nice, for a plane, for instance. Positive constant strength, rho to the n, right? Because this is n-dimensional. Huh? And this I will ask you for every rho and for every point in the hypersurface. Okay, so this will be the condition 4. Okay, and then the conclusion. Then, for every function, now the Sobolev inequality, for every function with compact support on the hypersurface, defining the Sobolev exponent now associated to the fraction S as NP, and here instead of N minus P, N minus SP, what we have is that what you can imagine, DLP norm, DLP star norm, P star S norm, BS star, and this is the volume, less or equal than a constant. And I'll tell you what the constant, let's write it here. It depends on N, S, P, and C star. All the ingredients above, nothing else. And then the double integral, it already appeared, right? These are the Dirichlet, the Gagliardo semi-norms, which are like the Dirichlet energies, right? But in the fractional case, you know that they are double integrals, and we have these differences. Now we have the kernel, that here is n plus sp, and then ddx, ddy. ddx, ddy. Okay? And 1 over p, and that's it, and this will be 5. And let's keep this for later. Okay, so this is the proposition. Oopa. This is the proposition. Okay. Good. So, in particular, all this is fine if m is equals Rn in Rn plus 1, the constant C star that depends only on n. So, so this constant here will depend only on n, s, and p, right? Okay. But in this version on surfaces, this constant C star for the moment depends on the geometry of the hypersurface, of course. So I still didn't prove a Michael-Simon inequality. Besides, remember the Michael-Simon, the local one, had an extra term with the curvature. Remember? And the curvature was taking care of the geometry. And then this constant became universal. No, I'm not doing that for the moment, okay? In fact, the fractional Michael-Simon Sobolev inequality, as the one we saw yesterday in the local case, it's an open problem still, okay? But I will come to this. We will know how to prove the fractional Michael-Simon Sobolev inequality for some surfaces. We will see which ones. This is the theorem, and now the proof is the simplest one I know. the simplest one that exists, and it's very clever and it's very precise. It's one proof that Bresis found and didn't, in fact, he didn't publish it, but then it appears in some books of his students, and it's great. You will see. It's very, 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 very simple. So, proof by Bresis. If you, he likes it now that we put it as reference and publish, and he said that the year should be 2001. Okay, that's what he told us. And then, but you can read it also. So he does it in a REM. But then, as you will see later, then it was adapted. We realized, I realized with Matteo Cozzi, we realized that it could also work on any hypersurface only with this assumption on the lower bound on the density. This is lower bound on the density. On the density, I have this surface here, M, right? And all this is in Rn plus 1. And I'm looking at I'm looking at this area here, at this perimeter here, right? And it shouldn't be too small, okay? It shouldn't be too small. X0 is here. The point is important that it's centered on the ball, right? It's centered on the ball, because if not, yes?
You have mentioned density. So the question is the inequality for needed for any row or only for sufficiently small row?
For sufficiently small, we could have also a version, but let's assume here for the nice statement like this, because I didn't say where was. I mean, if you have it for a small support, things will not be so nice, right? But because you will need to cover, it wouldn't be so nice. But there is a version, I think, in the paper. So the paper is CABRÉ Cozzi. It's called a gradient estimate. And we will come back to this paper, a gradient estimate, etc. And it appeared in Duke Mathematical Journal in 2019. Everything is in archive in my web page also, okay? Okay, so how does it go? Adapt it in here, two surfaces, two hypersurfaces, two hypersurfaces. So how the proof goes, it's very simple. You will see. You take 2 points and you say u of x is less or equal than u of x minus u of y plus u of y. The points are in M. The points are in the surface. In the surface. And now you take any positive radius and you integrate. And you integrate any positive radius, and you integrate. Always, I'll be using ambient balls, right? Ambient balls. Now I will use this was ambient balls. So now I integrate. I make the average with respect to what? In the ball center at radius, center at x. Now I fixed x. And I integrate on y. And this is, just to make it short, this is the same as this, ambient, always ambient, but I will not write it anymore, okay? But ambient. And I make the average, right? This is y, and then the same with the other term, which is this one here, average, and dr x uy ddy. Okay, this will be term 1, and this will be term 2, right? And now term 1, I bound it like this. I bound it like this by James. It's an average, so instead of power, since I want power p's, let's do it into power p. I could stay with power 1, but let's do with power p's. P, and here I have u of x minus u of y to the power p dy and 1 over p. And now I will introduce the lower density, And I will say that, no, not yet, the kernel. First, I introduce the kernel here. X minus y, n plus sp, n plus sp, right? Yes, ddy. And when I am at distance r from x, the kernel is very big. It's very big. It's much larger. It's much larger than what let me say here. Yes. So the radius. Sorry. The radius is smaller than x minus y. So r over the radius is larger than 1. That's what I meant. The kernel is larger than 1 over r. The kernel is larger than 1 over r. Okay. This is obvious, and I shouldn't forget this. I just used that this is larger than that x minus y is less than r, right? And now, well, we can continue already because from here, in fact, from here I can continue from here. So let's just use this, okay, for the term 1. And now I introduce the constants will depend only on those things there, as you will see. And now I use the lower bound because this is the intake. I take out this symbol and I have to bound by below this measure. Okay, this measure. I use this here simply the C star. Okay, and I have r to the n that will kill this n here. Okay, and then I take it out of the. I will take it out of the pth root, so I will have r to the s. You just check everything. I was careful, and everything is correct. Okay, so here the fractionals are semi-norm. P. And now the second term. What do I do with the second term? The second term I don't do nothing. I just do Jensen, very silly Jensen, which means that with averages I can say that that is less than the P star. And now I go to P star, PS star, ddy. With average for sure that is less than this, right? Yes, and now I take out again the average, and I use the lower bound of the density, and it turns out that then what you get, and you put out here, what you get is r to the power minus n over p star. Okay, well, just check that, and here there is a parenthesis here. Okay, and now we will do something, look how funny. We do something like, I don't know, like what we did yesterday for the Michael Simon. I'm going to choose a radius r that depends on every point x. And that changes at every point x. That we said yesterday with Matthew that it was a strong thing to do, and here we are doing it again. Can you remember another place where it is important? It is in Adams' proof of the Riesz transform bounds from LP spaces. The trick also appears there, I think. Now we can go, or I continue there, or we can go upstairs, right? Downstairs. Now I can erase this. And you can imagine which radius I take. Very easy. Just to optimize. Just to optimize in R, because R here is multiplying and here is dividing. And which is optimizing this is the same to choose an R such that then this term becomes the same as that term, or proportional to that term. Yeah, the same as that term. So optimizing R. And therefore, I will take for every x, I will take R of x. Well, let me just write it, okay? Now, we are not going to check the details, we will do last time. This is just algebra, so there is nothing to worry here. And here, I just copy. And then there is the fractionals. Still only one integral, not two integrals, still. So it's not the Dirichlet norm or the Gagliardo norm. Still only one integral on y. And here -1/n, it seems. You choose this, and then what you get, you plug it there, right? And still, this I still have it for every x, so it's still a pointwise estimate. Here we have our constant, and here you have. Now let me write. Yeah, I write this one first. X minus y and plus sp is y. I don't know if there is a power. Yeah, there is a power, 1/ps star. And then another factor, which is the LP star norm. dy, 1/ps star, right? No. Whatever it has to be, S over P, SP over N ps star. Okay, whatever. And now we are done. Now, just raise all this, raise it to the power ps star, and then integrate on x, and we are done. And here we will get the Gagliardo-Sobolev semi-norm, which is, let me write it because I still didn't write it, but it already appeared, right? The Gagliardo-Sobolev semi-norm, which is the double integral, right? The double integral of that u of x minus u of y to the p x minus y n plus sp dx dx dy. Okay, so you see, super simple, huh? The proof, super simple, and it works even in surfaces. It doesn't give the best constant. Yes, Moritz.
The question: if you in 5 allow or put in 1 minus s in front of the double integral, is it true you can then have it lower, so you could just have the constant independent?
This will come later. This will come right now in this same method. We will analyze this constant, but here you don't get it.
No, but you could modify the proof slightly so that it's possible.
Oh yes. Oh, very good.
But by choosing several radii and
the
sequence.
Oh, great. So what Moritz is saying is that in a second we will meet. We will see that the sharp Sobolev inequality has a constant that behaves, and it's important. You will see why now in a second. Like 1 minus s, okay, times constants. But as s goes to 1, what you want is that this, as s goes to 1, goes to the local Sobolev norm. For this, as s goes to 1, to go to the constant, so let's do it now. Let's write it here. Up to a multiplicative constant, but universal. So let me say. Now we are going to do s. We want to do s go to 1 in order to have something consistent. That means that we recover the local norms. Then for this to happen, you need to put here 1 minus s and a constant that depends on n sp, but doesn't blow up as s goes, it doesn't vanish and doesn't blow up as s goes to 1. So let's put it here. Constant that depends on n and p, and it's a positive constant, of course, not 0. Okay. For that, so this is a theorem. This is true. It is a proposition, and this, in fact, was first proved by Bresis and collaborators also. I think maybe Bresis and Milionescu, okay. But and what Moritz is saying is that with this choice we don't get this factor, so it's worse what we got. But he says that choosing better the radius, you can get this factor. Okay, so exercise maybe or not. Another choice. This I don't say this. Okay, this Moritz will tell us a reference. Okay, but we trust him, of course. Another choice of R of x gives the factor 1 minus s. Do you know if it's written somewhere, Moritz?
I think he again has a few. I'll check his thesis whether it's there.
Who?
The guy I mentioned before with the many names. His last name is Vogel.
Oh, okay.
But I'll check.
Okay, thank you. Check. You let me make an interrogation. But we trust you. Okay, very good. So now look what, well, u was a C1 function. Now let's take p equals 1, and approximate a characteristic function. So now take a subset of n, okay, bounded. So its closure will be compact, and approximate the characteristic function by C1 functions, and approximate to go to u equals, it's not a C1 function, but will have compact support, u equals the characteristic function of E. Okay, this is the function that is 1 in E and 0 outside. What did we get? What we got is that the measure of E, right? The measure of E to the power 1 over, the measure of E to the power 1 over Ps star, which is P equals 1. So n over n minus s, so n minus s over n, less or equal than a constant that will depend on n. Let's do it now in Rn, okay? Let's go now let's go back to the Euclidean case, okay? To the Euclidean case. So the constant will depend only on n and s. And here what we have is the this semi-norm. But now this is a characteristic of A. So this is 0 if x and y are in E. This is 0 if x and y both are in the complement of E. And this is not 0 only when one of them is in E and the other in the complement, and vice versa. But it gives you the same. So what you get here is this quantity that is this double integral, and from now on I will use this notation. EC is the complement of a set, okay? The complement. And here I will have d dx, d dy. No, I'm in Euclidean space, so I will write dx, dy, and here the kernel. But now n plus s, because p equals 1, okay? And this is called the fractional isoperimetric inequality. Not with the best constant, but okay. And let me just tell you that it is known that balls are with a volume constant, with fixing the volume, balls are the it is known that balls that under given volume, or given measure, balls are the unique minimizers of fractional perimeter, because this is going to be called, this is next section, but okay, this is going to be called fractional perimeter of E. Fractional perimeter. And then, when was this proved? Well, Bresis also made us realize something that we forgot, that we didn't know. Well, not me, but even Frank and Seidinger and maybe Lieb, I don't know, that there was a very older paper by Garcia and Rodenick from 1974, where they prove with a rearrangement, they prove that balls minimize. So they prove the best constant. They find the best constant. So they proved inequality with best constant. And then Frank and Seidinger in 2008 proved that, probably they give another proof, like shorter and nicer. Yes, I think so. With the hardly, yeah, they give another proof. And they also prove the uniqueness, that balls are the unique, okay? I think that there is another proof, plus uniqueness, okay? I just wanted to tell you this, but we are not going to get into this. Okay. By the way, no open problem. As Moritz said today, there is no IVP. He said there is no Alexandrov-Pachelman-Pucci theory for in the fractional case. Right? You said that when he was speaking about non-divergence operators, non-divergence form. As nice say, at least as in the local case. And that's why my proof of geometric inequality that we did yesterday, the first thing we did, there is no analog in the fractional case. So that one would never, okay, so no, in this respect, right? No, there is no analog of the AVP proof of the classical isoperimetric inequality. So theorem 1. From yesterday. In fact, if you remember, today Moritz spoke about variational equations, non-variational equations. I wouldn't dare to say which ones are more important. I think both, and which one I like more, I don't know. I like both a lot. But you may like one more than the other. There is no problem with that. I like both. But what is important is that the methods, it's good, even if you do variation, if you only do variational stuff, it's good to know both methods, because both are very powerful and they can be useful in different situations. And I believe that that proof of the isoperimetric inequality yesterday that is surprising because it's so short, it's because it combines both things. Because if you remember, I started solving a problem and saying there is a solution because of the compatibility condition, because of the divergence theorem. So I use the structure of the Laplace operator, the variational structure of the Laplacian, to integrate it by parts and take the Neumann data. That was the variational part. And then later, instead, I used the method of Alexandrov of touching planes and looking at the gradient, and that's a purely non-divergent method. And in the proof, at some point, it appeared the determinant of the patient, which is the Monge-Ampère operator, which is the excellent, by excellence, the non-variational operator. Okay, so that's, I think that's why also that proof is so is good. But for the non-local, there is no one of the classical. I didn't finish the flat sentence, but you finished, right? For the non-local, in the non-local setting, in the fractional setting. The closest thing was done by Caffarelli and Silvestre to avoid the IVP estimate and go to the Krylov-Safanov theory, the beautiful CPAM paper. Okay, but let's stick to what our things. Next section, fractional perimeter, but we already have it here, right? So next section is fractional perimeter and I guess and non-local mean curvature. Okay, so this section will be a little, there will be not such a strong theorems as before or results, but I think it's important for some of you to get acquainted with these things. So let's try to go a little quick. Anyhow, you stop me if needed. All this as introduced in the seminal paper. So I tell you what is the seminal paper by Caffarelli, Roquejoffre, and Savin. Okay, so this is, we will be speaking several times now about the paper of Caffarelli, Roquejoffre, and Savin, CPAM 2010. Yes. So definition 5 is fractional perimeter, right? Fractional perimeter, you already have it there, but now, and you will see that it's not by pleasure or to confuse you, the other way around. I'm going to change notation. It's important. For the dimension, you will see why, yeah? Several times. This will be useful several times. This will be an open set. And n later, n sometimes will be n, small n, or n, I will think of n, or it will be n plus 1. So okay. So I'll be in Rn, small n, and I will apply things with capital N equals n, small n, or n, small n plus 1. So I think it's very useful to use now this. And also you will see why to change the fraction, instead of calling it S, let's call it alpha. Because later, sometimes I will have alpha equals S, and also other times I will have alpha equals another thing, another function of S. So let's do it like this, and let's define the perimeter, the fractional perimeter of it, and it's just like that. But now I put a constant. There was a constant here also. Well, there was a constant. Let's put the constant, and we do, of course, E complement the interactions, right? So I have this set E, and I'm looking at the interactions of X and Y. And what you have to realize is that this kernel, of course, is, and now here you have n plus alpha, huh? Like here, yeah, n plus S, n plus alpha. Of course, this kernel is singular, and therefore, it's singular, and therefore, when X and Y are very close, but for X and Y to be close, you have to be close to the boundary, because X is inside, Y is outside. You have to be close to the boundary. And the kernel is singular, and what you are seeing is that pretty much you are making an integral that mainly contributes in a neighborhood of the boundary of it. And therefore, you have the hope that you may converge to the perimeter. And that is true, but with the right constant. So we are going to define this with a constant you can find in the papers, right? And the constant, well, maybe not in the paper by Caffarelli, Roquejoffre, Savin, because they will fix alpha probably there, but you find it in other papers. And the constant, the important thing, is that behaves as 1 minus alpha, as alpha converges to 1. And then the perimeter converges with this with the right constant here, the perimeter converges exactly, as alpha tends to 1, converges exactly to the perimeter, huh? But there is this factor that is the same as Moritz was saying here, 1 minus s, 1 minus s. Okay. If E is bounded, okay, so now when is this fractional perimeter bounded or not? Okay, of course, a plane has infinite perimeter. Classical perimeter, it also has infinite of this, because these interactions, x and y, they are repeated all over, so infinite. But note, if E is smooth and bounded, then this is finite. If E is smooth and bounded, then this is finite. Why smooth? Well, you should practice now a little. You should practice a little with these interactions and check when this is integrable or not. If I have a corner, what happens? It's integrable, right? Yeah, if I have a corner, it's integrable. But I have a cusp. I'm more used to think about the fractional Laplacian. If I have a cusp here, this double integral, I'm not so sure. Probably yes, also, because probably. Let me just say that. I didn't think about this. I don't want to make something, don't say something wrong. That's what I wanted to keep, right? That's what I wanted to keep. So I just finished here. So maybe I continue here. Okay. Now, we need to derive an Euler-Lagrange equation for minimizers of the fractional perimeter. In the classical case, the Euler-Lagrange operator associated to classical perimeter is the mean curvature, right? And minimal surfaces have zero mean curvature, and under a volume constraint that is like a Lagrange multiplier, the mean curvature is constant, like balls have constant mean curvature, CMC surfaces. We need to do the same here for this funny functional, which is a double integral. And I want to give you a flavor without doing the details of how do you do the Euler-Lagrange equation, because I'm sure that some of you have never done this. I don't know if I've done it in a lot of detail ever, neither, but yesterday I did it a little, in some detail, okay? So now we go to do the Euler-Lagrange equation. Euler-Lagrange equation of fractional perimeter. Okay, this I said already about the Garcia-Rodemich and Freund-Salinger, very good. So what am I going to do? I have to do a calculus of variations, right? I have this set E, and now, but I don't have functions now, and I have sets, okay. And I have this set E, and now I'm going to perturb it a little, but in color. I'm going to perturb it, and just perturb it a little here, perhaps, and maybe I go back here, and I do like this. And my new set will be, in red, will be what it was, but now this I remove, and then maybe this I add. So I added a small piece and I removed a small piece, okay? Good. And now let's make a notation to not to write all that thing. This is the Caffarelli Roquejoffre Savin notation. Let's call L of AB the double integral of the kernel of the kernel when in a set A and B, okay, which is a symmetric, thing. Remember that, okay? And then to simplify your life, if you have to do something with these things, just when you have something like this, just divide the whole thing in another column. Divide the whole thing in disjoint sets. And I don't care about with the drawing is very good, and I'm not going to lose time, which means that there will be 4 disjoint sets. E1, E2, E3, E4. E1 will be here, E2 will be this one, E3 will be this one, and E4 will be this. Disjoint, and that they fill in everything. So there is no doubt. And now you will see why this will simplify my life, okay? Because then I say, I have to compare the perimeters, and what I know is that the perimeter of E is less than the perimeter of E epsilon. It's a perturbation. This is the E epsilon is in red. E epsilon is in red. Okay? So what is the perimeter of E? Perimeter of E up to a multiplicative constant that I forget is guys inside with guys outside. But guys inside are either of E, E1 or E2, and outside E2, E3, E4. So E1, let me copy because I will have to rearrange things. Plus E1, E4, and then E2, E3, plus E2, E4. And instead, the perimeter of this guy is E epsilon. Inside is E1 and E3. E1. In fact, you want to see what I do when I work these things out. I forget about the L and I say E1 and E3. So E1, E3. E3 is inside, and outside are E2 and E4. So E2, E4, E2, E4. And this notation means that I'm doing the coupling of these two, and these two, and I go faster like this, okay? And now some guys simplify. This one simplifies with this one. And another one simplifies with another one. This one simplifies with this one, okay? So what I get is that 0 is greater or equal than E3, E1. Let me write it like this. Huh? This is formal, but E3 minus E4. And then minus, I'm copying, E2, E1 minus E2, E4. And now I will write what is this. And this is the integral on E3 dx Rn dy. And now here I will write the characteristic of E1 at y minus the characteristic of E4 at y, x minus y, n plus alpha. And you agree with me that these are the two first terms. I'm sure you agree. And then you also agree that these ones are these. And here the same, right? The same, this difference of characteristics. And now think that E2 and E3 are going to be very small. Very small. And for instance, let's do the case of the isoperimetric problem. Volume constraint. For instance, isoperimetric problem, for instance. Isoperimetric problem. Volume constraint. Which means that the perturbed constraint. So the perturbed set, E epsilon, must have the same measure as E, and therefore the measure of E2 is the measure of E3. Which means that the measure of E2 is the measure of E3. These sets depend on epsilon, are very small, I can make them contract to a point. So now I give you a point X on the boundary, and now I'm not doing the details, but a good exercise, did I write it as an exercise? No, but a good exercise, this doesn't have a number, would be to make the details, or if not, look for them in some reference. Do this and make E2 epsilon and E3 epsilon converge in a way, converge to a point X on the boundary of E. And then not something, to what does it converge this? This converges E1 and E4. E1 and E4. They are not E and E complement, but this will go to 0 and this will go to 0. So I expect this to converge as epsilon goes to 0 to converge to the characteristic of E minus the characteristic of the complement of E, right? And the same here. And the same here. So at the end, the limit should be the integral in Rn. We will discuss now this 1 second. And now I will change the sign. I will change the sign. You will see why later. This quantity depends on X. This quantity, it will be a principal value. Now we discuss what is principal value, or perhaps all of you already know principal value. Let's talk a little about it. Yeah. With a constant, with an appropriate constant that depends on n and alpha, this is what we will call, by definition if you want, we will call the non-local mean curvature of order alpha of the set E at a boundary point given X on the boundary. And this is a definition. I wrote it here, definition 6. Non-local mean curvature at X. And there is a minus here, say, if this quantity is constant and the measure of this is the measure of this will go to 0. But okay, because here I wrote this inequality, but as epsilon goes to 0, since I'm making a critical point, this should go to 0, not only have a sign, okay? So this inequality will become an equality equals 0 as epsilon goes to 0, because we are doing the first variation, right? You see, I just wrote inequality for minimizers, say. Okay, you understand what I mean. I'm pretty sure that everyone. So since this happens like this, for this here, what I will have is that non-local mean curvature is equals to constant for constraint minimizers. For constraint minimizers. And these surfaces, we started studying them, and we call them constant non-local mean curvature surfaces. Constant non-local mean curvature surfaces. So now we have to look a little at this quantity. Let's look at it in more detail. But first, let me write it in different ways. Where I am? Where am I now? Where am I? I'm here. Okay. No. As alpha goes to 1, am I going to say this somewhere, or it's not written here? No, I said it for the perimeter. But good, thanks, Alice. No, as with the right constants, as alpha goes to 1, this goes to mean curvature. Okay. So let's write it somewhere else. I want to keep this proposition. Good. Remember that when we had the fractional Laplacian, you don't have n plus alpha. You have n plus 2s. You don't have n plus s. For the fractional Laplacian, you have n plus 2s. So now it comes in fact. Now this comes now because I'm going to write the non-local mean curvature as a fractional Laplacian in a rank. Yes. Of the differences of characteristics, right? That appear, yes. This difference of characteristics, it already appeared. Raf was speaking about these functions, for instance, the difference of two characteristics. And then the extension and things like this. But now we are not making any extension. So, this quantity is the notation I use there, alpha E, yes, right? Alpha, it's up there. Alpha E, correct me?
The of the integral
N plus alpha. Okay. And this is, it's not the alpha half Laplace, it's the alpha fractional Laplacian, it's the alpha over 2. So this is the same. We will speak about principal value and why is this well defined in a second. Let me first write more things that may be clarifying. This is the fractional Laplacian with exponent alpha over 2 of this characteristic function, a difference of characteristic functions computed at x. Okay? So an alpha over 2, and this is what Alice had in mind, alpha over 2, note that alpha over 2 is less than 1/2. Okay? Right? And alpha tends to 1, as alpha tends to 1, alpha over 2 tends to 1/2. And what happened is that Alice had in mind that the mean curvature, you recover the mean curvature when the fractional Laplacian goes to 1/2, right? So that's the answer to your question. Now we will look at that, and then an exercise here, exercise 4, but maybe it should be 5. This we could be 3 B's there. This one there, exercise 3 B's. And now exercise 4 for another way to compute the non-local mean curvature as a surface integral. So I have this set E here, I have this point X, and to compute the non-local mean curvature, I make that integral in a rank, like a fractional Laplacian in a rank. But now I want to compute surface integrals. Why not? Why not? And the formula is very easy. It's x minus y times the normal to E at the point y, and then the kernel, n plus alpha, dvy. And this will be, prove this, exercise 4, prove it using you can imagine, right? You have to pass from an integral in a rank that you can imagine as an integral here minus an integral here, you have to pass to a surface integral. So you have to use the divergence theorem. It's an easy exercise, huh? Very easy exercise. Just compute the divergence of x minus y with respect to y of something like this. Okay, good. What is the meaning of this? This fractional mean curvature is very, very intuitive what it is. Because think, I like to see it here also. I like to see, this is useful for some other things, but we will not use it. Caffarelli, Roquejoffre, Savin also don't use it, but I use it to study CNMC surfaces. But no, let me look at that, and let me write it, say, in spherical coordinates, right? Spherical coordinates. So C and alpha E. No, sorry, integral inner. I thought I'm always looking, since I was writing down there, I'm keeping looking here and I have it up there. So let me erase this. So think of that integral of the non-local mean curvature in spherical coordinates, and then you will see very well. You will see very well what you are doing around x. You fix the point x. You take spherical coordinates, center at x, and spherical coordinates, radial coordinates, polar coordinates, and then what you see is that on every sphere you count. You look at the difference of the surface area, so outside and inside. So now I will do this. Bring some of these guys here. I will do this. I will take a radius r. I will look at this sphere and I will look at the part outside T, the part inside T. I will see the difference between this surface area, and then later I will integrate on the radius, giving much more importance to the points which are to the radius which are small, and much less importance to infinity. So this is like will be capturing a variant of the usual mean curvature, right? So this you can imagine like this from 0 to infinity. dr. What is the kernel right now? Spherical coordinate is r to the n minus 1. So it will be n minus 1. It will kill this n minus 1 minus alpha. And now integral on the boundary of the ball of radius r center at x, and now the differences of what? The differences of okay? The differences of. Did I put this correct? Here I put it E complement first, and then here I changed the order. Yes, I think it's correct. I put it like that so that balls have positive curvature. Balls have positive curvature. Yes. Balls have positive curvature because the complement has more area than inside. You see? And here, so it's a complement first, and then. And now we can understand even when it's well defined. This is very nice because you see, this is not integrable. This is not integrable at 0. So this has to vanish. This must vanish at least at order alpha, and that's not enough as r goes to 0. And this means that the ones and the minus ones have to cancel each other as r goes to 0. So a corner here is very bad. It has infinite non-local mean curvature at this point, and also mean curvature. Because the ones and the minus ones don't cancel, and therefore this is infinity, you see? So you will need to have a set of if E is a set a little better than C alpha, of C1 alpha, sorry. First, it will need to have a tangent plane, and then even a little more. Correct, Moritz? Yeah, I think so, right? Yeah, C1 beta with beta, for some beta bigger than alpha, then it's fine. Then it is fine. Okay, let's not waste more time on this. But if you have a question or right, I think it's good. So where did this appear? This non-local mean curvature appear for first time in the paper of Caffarelli, Roquejoffre, Savin? No, in fact, it appears in a previous paper of Luis Caffarelli and Takis Ouganidis. So, so non-local mean curvature appeared first in a paper of Caffarelli. I think they have two papers, but in one of them, I didn't write the years. But a little before 2010 or around 2010, 2009, perhaps something like this, more or less. As limit of well, what is called threshold dynamics, but let me say of some type of fractional of mean curvature flow with long range interactions, or some type of fractional mean curvature flow. So mean curvature flow. In fact, what it is called the threshold dynamics. Threshold. I don't know if I know how to write threshold. It's a way to discretize mean curvature flow and compute. It's a very important method to compute mean curvature flow. But when you discretize, you see, when you discretize, you are no longer local. Have you thought about that? When you discretize a problem, I mean, the thing of local and infinitesimal, what is this? This is a trick of Leibniz and Bernoulli and all these guys, right? That allows us to simplify things and write the Newton's equations, but life is not local and nature is not local. And when you put in a computer, you are not local anymore, because you discretize, you are not local. So when you do threshold dynamics, you can be more local or less, depending if, I don't know, if you do one Runge-Kutta or another or whatever, right? So think that this also appears in computers. And in fact, so they change the threshold dynamics to make it a little more that you see you are less local, and then as a limit of the parameter, they got the non-local mean curvature flow. First, non-local mean curvature, first time that it appeared in this paper. Then it is studied in the paper of Caffarelli, Roquejoffre, Savin. But let me tell you, before going ahead, let me tell you that it is also very important. The fractional perimeter had so first is fractional perimeter and then non-local mean curvature. Fractional perimeter, it had already been considered before Caffarelli, Roquejoffre, and Savin. And for instance, there are very important papers in image processing. So, and I want to mention this. Non-local fractional perimeter methods are very relevant, have been, I mean, that this is not so recent, even before all these analyses that we are doing, have been relevant in, and I will give you a reason why, in image processing. Well, first, when you have a picture and you treat a picture or an image, it's not local, it's pixels. I mean, you are already discretizing. And they realized that sometimes, but the mean curvature flow is very important in image processing, because you want to when a picture, you know, when a picture is too expensive, that it has too much resolution, and it's too expensive, what you will do is to run the mean curvature flow for a very short time, of very short, just to diffuse it a little, and that it's not so expensive, okay? So mean curvature flow is very important in image processing, and they realized that they could do it in a non-local way, and this was the group of Jean-Michel Morel and the people in Mallorca, in the Balearic Islands, Saludas and Tomeu Coy, very important papers. And in fact, and Photoshop knows about this, okay? Photoshop knows about this. Let me give you one of the reasons that I learned from Joaquim Serra, who was when he was doing my movie, he was still doing the PhD with me, and it's very nice, this. Okay, so this is an image, and it has pixels, okay? Of course. And this is a square picture, 1, 1. This measures the square root of 2, but it has pixels. So it has pixels, and this line, I cannot picture this line like that. So this is black and this is white. Black and white. I mean, this is the boundary of an object, black and white. But I have to approximate it by the pixels, and this will be below, they will be black, and above, they will be white, for instance, okay? And this size is going to be, this size here is going to be epsilon, very small, epsilon, okay? So let's compute perimeters. Let's compute the perimeter, classical perimeter of the picture epsilon, at level epsilon, but classical perimeter of this guy, black and white. What is the classical perimeter of this set here? Two. What did you say? 4. Well, I guess you're right. 2. Well, 2 plus 2 plus 2. 2. Yes. Yes. Just one. I mean, the diagonal, no, but you're right. The diagonal, you see, it measures the vertical things measure 1 and the horizontal things measure 1. Okay? And this is 1 plus 1. So you are right. I wrote 2, but it would be better to write 4. Okay? I will correct. Okay? And this is larger than square root of 2 plus 2. And now we are, now this could be an exercise also. Yes, this is a nice exercise. Exercise. You can tell me the number, please. Where did I say an exercise? 5. But where is an exercise?
Your left, no?
Here. Thank you. Compute the order of the perimeter, fractional perimeter of this guy at level epsilon, and do epsilon go to 0, and check that this will go to the fractional perimeter of the diagonal, that as alpha tends to 1 converges to the classical perimeter, which is the real thing, square root of 2 plus this converges to the perimeter of the diagonal. This is known. This is a lemma. I told you this is known. This is a proposition. Okay, here there is everybody satisfies this. Everybody satisfies this, and this is square root of 2 plus 2. So the fractional perimeters are capturing the real perimeter much better than if you at the epsilon level you compute classical. So the exercise is to check this, right? This one you don't need to check. I mean, this is a proposition. This we know. You can learn the proof, but this is the point. Thanks to interactions. Okay, and I think we can finish this now, this section, just with this. Oh, that that I will need tomorrow. That I will need tomorrow, but it's okay. So, but now in minimal surfaces, what is important? The isoperimetric problem and to find constant mean surfaces. I mean, the isoperimetric problem with constraint, with volume constraint, good. But then also minimal surfaces, right? Minimal surfaces. What are minimal surfaces? Minimal surfaces is the plateau problem, right? So the plateau problem is, the minimal surfaces is that you give me the boundary of a wire in a REN, right? N minus 2 dimensional, for instance, in a REN, N minus 2 dimensional, and I like to find the surface N minus 1, or let's do like this, okay? Let's do like this. And I like to find the surface Mn that has less perimeter and that has as boundary values this. We need to do the same thing for the fractional perimeter. So we need an analog of this. This is the plateau or the Dirichlet problem. So we need an analog that this is what Moritz discussed today in a way for the linear operator, for the quadratic forms, right? For the linear operator, for the fractional Laplace. And now we have this geometric operator. We need an analog in the fractional setting. And this was done for the first time by Caffarelli, Roquejoffre, and Savin, 2010, the paper I mentioned. And of course, in the fractional setting, so let me now make another picture. Let me take a ball here, omega, or something, it doesn't need to be a ball, right? And I am where? I am where now? Let's fix the notation. I will be in a Rn, right? I will be on the blackboard. The blackboard is a Rn, okay? And if I was local, you tell me, you give me 2 points here, and I find the minimal surface, right? 2 points. But in the non-local setting, what you will have to give me is not 2 points, but what you will have to give me is an exterior data, like in the talk of Moritz, or in other talks. So you will give me an exterior data that it may be aligned, or maybe not, it's not aligned. And maybe it goes to infinity. Okay? And therefore, and what you give me is outside omega, because we will be talking about the Dirichlet problem in omega, outside omega, you give me a set. So let's start writing. We are given, now I don't know if I like the notation I use here or I like the E and the F. Later E, the minimizer should be E. The minimizer should be E. Okay. Okay, let's not complicate. We will see them later in the lecture notes. Okay. Let's now be given a set F in a Rn. And I look at sets in a Rn such that they agree with F outside. So outside omega, E minus omega, outside omega, E minus omega is the same as F minus omega. So I need to, this is the exterior data. And then inside you can do it in different ways. This is one possibility, this is another possibility, and E will be this thing here, okay? This thing here. And this will be another E. But outside, they agree, okay? And then what we would like is to, well, let's take this class and let's minimize fractional perimeter and let's see what happens. Because there is something wrong. There is something wrong, right? Because this E that I draw, that is infinite, it has infinite perimeter and it has infinite fractional perimeter. So I look again at the interactions. Again at the interactions, and what are the interactions? So this is E now, down here. This is omega here, is of the box that is fixed. And what are the interactions defining the fractional perimeter? N alpha of E. Are these integrals of dx dy, right? And x inside and y outside. But okay, then this means this x can be here inside E and inside omega, or can be outside omega, and the y can be here or can be here. Let's write. Well, I don't know what to write. Let me write like this. One. So there are these interactions. One. There are these interactions. Two. There are these interactions. Three. And there are these interactions, 4. And since these interactions for one the x is in a bounded region, omega will be bounded. For the interactions 2, well, for 1, both are in a bounded region, both x and y. For 2, x is bounded and y is not bar is not bounded, but x is bounded, and this makes the integrals the fractional perimeter interaction to be well defined and finite. And this one also. The problem is the interaction 4. The problem is 4. That is the interaction when x dx dy, and when x is outside omega, and y it's also outside in the complement of E, but outside omega. And this gives you infinity, of course. Gives you infinity. But everybody agrees outside omega. All competitors have the same infinity here. Because all competitors agree with F, the given set, outside omega. Okay? So I could say I'm a physicist, and I say, okay, well, all this infinity is the same for everybody. So I forget about it, okay? And I renormalize. So what they do with now, what we are going to do is just forget about these interactions, and we are going to define the relative fractional perimeter relative to omega. So definition, right? 7 is the fractional perimeter relative to omega, relative to a box omega, relative to a box to omega. Okay, and so omega is given, right? And omega is given, and you have a set E in a Ren also, and you defined. It's not contained in omega. Eh? E is this guy. Yeah, remember, E is always this guy. For F, they have this. You have to think of this like this. It's not contained. And then we define the perimeter and alpha of E, but inside omega or relative to omega, and these by definition are going to be up to multiplicative constants that in one paper you may care for them, in another paper maybe you don't care what they are, it doesn't matter, depends what you do. The interactions 1, 2, 3. So inside, what I say inside omega, but always one inside and one outside. But now inside omega plus inside omega and outside omega and outside E. Outside omega and outside E, I will write it like this. Outside omega and outside E. And then the third is outside omega. But in E, all these guys are in E. And all these guys are not in E. And then inside, but not in E. These three. And this is 1, 2, and 3. These are 1. This is the 1, and I don't know if this is the 2 and the 3 or the 3 and the 2. And this is just a definition, huh? Just a definition. And then now let me tell you, and we finish here, let me tell you what the paper, Caffarelli, Roquejoffre, Savin, which is a very important paper, seminal paper, right, proved. What they prove. What they prove is many things. And it's really an analog of many things of classical minimal surfaces. First, they prove so what you want to do is to minimize this among sets which agree with a given set outside omega. This is the plateau problem, okay? And what they prove is the existence, first thing, existence of minimizer. So, lower semi-continuity. And this is not difficult as you can imagine. This minimizer, we will call it a non-local minimal surface, minimizing non-local minimal surfaces. Then they prove something that tomorrow I want to I want to indicate how you prove this because it's very beautiful. It's the same proof in the local or non-local case. The density estimate, okay? Next section will be next section. And the density estimate is what we will tell me. It will tell me that a non-local minimal surface cannot do things like this in a unit ball if it passes through the origin and have this measure very small. It will tell me that this measure cannot be very small, and therefore it will have some measure. And if this has some measure, and if this has some measure by the same reason, then the perimeter of this has some weight, has some measure also. And this is what we need. Remember, this is what we needed in the beginning of the talk, proposition 4 here. So the density estimate will allow me to, it will give me 4. The density estimate, it will give me 4. I will be very happy because then I will have, well, the density estimate plus the classical isoperimetric, relative isoperimetric inequality. I will comment this more tomorrow. Let's continue because we have to finish. Density estimate, then the Euler-Lagrange equation in the viscosity sense. What does this mean? This is perhaps the darkest and most difficult part of the paper. Darkest. Well, we all believe it's a little dark. It's a little or obscure. It's a very clever proof, but quite difficult to understand and not very clear. What does it say, the proof? Is that we are taking a minimizer. This minimizer is not going to be regular. In general, it's infinity, like minimal surfaces. So you have to make sense. You have to make sense of the non-local mean curvature being 0. And pointwise, you cannot dream for this to have it pointwise everywhere on the boundary. So in fact, the best way here at this level is that they check it in the viscosity sense, okay? And the proof is quite difficult. Raf is around, or Raf? Yeah, Raf. So we will not have time to do foliations and calibrations. That was the last section. We will not have time, unfortunately. Maybe in the lecture notes we can put it. But one of the main things about what I did on calibration, on local calibrations, is one application that is to simplify very much this proof and give it like very natural and very, thanks to the calibration. Okay, let's continue. This was just a side and a part, okay? Improvement of flatness. This is like Harnack inequalities. Then extension problem and monotonicity formula. Oh, very important, right? Because in minimal surfaces, you need the monotonicity formula for many things. Open problem. Well, let me write it first. Let me write it. Can I take, Zara, can I take 2 minutes just to finish this section? I started late, okay. Extension problem and monotonicity formula. You know what is the extension problem. You will take characteristics, you will take your set E, you will take 1 here, -1 here, and we will make the harmonic extension, the S harmonic extension or the some harmonic extension, okay? And thanks to the extension problem, they can prove very easily the monotonicity formula, that it's an analog of the monotonicity formula for minimal surfaces. It's still an amazing open problem to prove the monotonicity formula downstairs without the extension. So open problem. I tried a lot with, but many people tried. I tried with my students, also with my postdocs. Open problem, prove the monotonicity formula downstairs. You know what I mean by downstairs, right? In this non-local world, when we do say downstairs, it means without the extension. And then dimension reduction of Federer, dimension reduction, and then the whole program of minimal surfaces goes the same, and they prove this theorem. The theorem that they proved is theorem that they prove, thanks to all this, is that minimizing non-local minimal surfaces in a box, right, in omega, for n, are C1 alpha. The alpha is the alpha, I guess. Yes. The alpha is the alpha, or the alpha is not the alpha? I have an alpha here, right? I have an alpha. And they will try, what do they prove? C1 alpha or C1 epsilon? I would say C1 epsilon, but I need to check, okay? C1 alpha. I'll be safe, and like this, I'm through. For some small epsilon, okay? Depending on n and alpha. Away, except for a set of Hn minus 2 of dimension, of finite Hn minus 2 measure, or of finite finite. Let me of dimension n minus 2 in the Hausdorff set. Of dimension, let me write it as I wrote here. Of Hausdorff dimension n minus 2. Okay, this to be checked. I don't think, because they use S instead of alpha, and then they write alpha, I guess. But I don't think so. Let's leave it like this. We'll check. Let me just say to finish that later, after this work, you can ask if you can improve this. For instance, in the classical theory, this is n minus 8, because there is the regularity theory of minimizing minimal surfaces up to dimension 8, which is it's not easy to find, to prove, and this is open very much in the fractional case. In the fractional case, this n now can be done to be n minus 3, but and then there are some results when alpha is close to 1. For minimizers, you can go all the way to n minus 8, but with compactness argument. So the theory is far from being, the cones are far from being classified, okay? And the people who contributed more were Enrico Baldinocci, Ovidio Savin, Alessio Figali, Joachim Serra, Eleonora Cinti, myself a little bit, okay? So that's all what I want to say, and then tomorrow, well, we'll continue with one thing or another. Thanks for your attention.
Questions?
Yes.
Good. All right. Thank the speaker again.